Hello, and welcome back to Shiksha DaCosta. Today we're going to take a look at exponential relationships in the real world. Today we're going to learn how to create an equation of an exponential function from a real world situation. And we're also going to look at the domain and range of that situation. You're good at this if you can identify an exponential function, especially if it comes out of a real world application involving growth or decay. And if you can explain any restrictions that the context of that situation places on the domain or on the range. To start off, let's think about this in a way that warms us up. Let's say you run across a store and you see a running out of business sale. In 1 week, everything must go. And they're planning on dropping the prices in their store every day by 10%. You think, okay, great. We have 7 days. How much of a discount do you think you'd get if you wait until the last day? Will it drop by 70%? Let's take a look. Pause the video here and see if you can figure out what that final discount will be. Well, let's say you show up there, that's day 0, so everything is still full price. But if you go there the next day, you know that you will pay 10% less than you would over here, and that would be 90%. So you'd still get a 10%, you'd get a 10% discount on this first day. On day 2, are you going to pay 80%? Is it going to drop by another 10? Actually, no. The store owners are kind of sneaky. They know about exponential relations. And so they only promised that the prices in the store will go down by 10%. So they won't go down by 10% overall, just whatever it was the previous day. So if something cost $1 on day 0, on day 1 it costs 90 cents. On day 2, the price has to go down by 10%. And 10% of 90 cents doesn't get you down to 80 cents. The new price is only going to be 90% of what it was yesterday. And whenever you see the word of, that means you need to multiply by what? By 90% as a decimal, which is 0.9. So on day 2, you pay 100% times 0.9. That was how we got 90% for day 1. And then multiply that by 0.9 again. And if you do that math, you'll find out that actually you're going to pay not 80%. That's wrong. You're going to pay 81%. You started at 100% of the price, and that dropped, that we had to multiply that by 90% 2 times, once, twice. On day 3, we'll multiply it by 90% a third time. And notice it doesn't drop to 70, but 72.9%. On day 4, we'll multiply by 90% again. On day 5, on day 6, and finally on day 7, we have the price has dropped. And I'm not saying it's not considerable, but instead of dropping by 70% all the way until it got down to 30%, the prices have only dropped to 47.8% of what they were. So about 52.2% of a discount. Still really good, but maybe not as much as you thought when you decided to wait all 7 days. This is an example of a situation that involves a real-life exponential relation. Whenever something increases or decreases by a percentage, every time that discount or that increase applies, the relationship that it creates is always going to be an exponential one for this reason. In this next example, the population of Toronto has increased by about 1% every year since 2001. In 2001, it was 2,481,500 people. Let's see if we can predict how many people will there be in 2047. So in 2001, so 0 years after 2001, we know the population. And if we want to find out how much is it going to be in 2002, we have to take this figure and increase it by 1%. So in 2002, the new population will be 101% of what it was the year before. It is going to increase by 1% to 101%. And how do we say 100%, 101% of something? The word of tells you that we need to take that thing, that number, and multiply it by 101%, but we're going to have to convert that to a decimal, and that is 1.01. So if I take 2001's population number and I increase it by 1%, I get 2,506,315 people. After 2 years, I would have to multiply this number by 1.01. So the new population that I got here is the population from year 1 times 1.01. Or if I want to express it as one operation, if I want to skip this step, I'm taking the population year 0 and increasing it by 1% 2 times, once, twice. And if I want to increase it many, many more times, I can understand that, okay, I will just keep having to multiply it by 1.01 again and again and again. So the population in year n will be the starting population times 1.01 n times. And when you repeatedly multiply, that's when you use a power. Now, 2047 is 46 years after 2001. And so I have to increase it by 1% 46 times. And that means if I evaluate this, I can estimate that the population of Toronto will be 3,961,128 in 2047. Exponential functions in real life can either grow, which means they are increasing, or decay, which means they are decreasing. A growing formula sort of looks like this: a times 1 plus g to the power of x. Remember that the value of the function f of x is the final amount that will be there. A is the initial amount, or we sometimes call that the y-intercept if we're graphing it. G is the growth rate in a percentage. But when we're using it in our formula, you have to remember, and this is a very important step that is very easy to forget, you have to convert that into a decimal by dividing it by 100. And x is the number of growth periods. However, if that relation is decaying, in other words, we're measuring a quantity that is going down, the final amount remaining at the end, of course, is f of x. A is still the initial amount, but the growth factor is not 1 plus the growth rate. It's 1 minus the decay rate. It's still expressed as a percentage, but it's like a discount, right? It's something that's going down. So we call it decaying. And once again, you do have to convert that to a decimal. Now, in real life, whenever we're making a function out of a real life situation, you always have to consider the domain and range. What numbers make sense to use? What numbers really don't make sense to use? And so you may have to limit that domain and range based on that situation. In this example, we have a culture of bacteria that's in a petri dish, which is one of those little clear discs. And the bacteria doubles in population every hour. It starts out at 1,000 cells, and eventually it will overflow the petri dish once it hits 16 billion cells. You might say, okay, great, good luck, culture of bacteria. Good luck going from 1,000 to 16 billion. But we're going to see when that actually might happen here. So we're going to create an exponential relation for this data. And then we're going to identify its domain and its range. And I'll give you a second here. Pause the video and then see if you can come up with the equation of the function and then its domain and its range. Right? So remember that a exponential function is really easy to create. You just need the initial value, that's 1,000, and the growth factor, the number that we are multiplying by, in this case is 2. We are doubling it in population every hour. So every time t increases by 1, t is the number of hours, obviously, we will multiply by 2 one more time. And so that's really, really easy to create. For the domain and range, though, let's see. The domain is, what's the independent variable here? T, time. Okay. Next, are there any limits on time? Well, we're not going to measure time before we start the actual experiment, before we start recording. So we can only measure the amount of time that has passed since the start of the recording. And that has to start at 0. Now, it's unclear what the time limit is going to be, right? Is there an upper limit? Like, does time have to be less than a certain value? I think there will. At some point, the dish might overflow, but we don't actually know when that is going to happen just yet. We haven't solved for that. So I'm just going to leave it the way it is now. For sure, I know at least that I can't have negative numbers for time. But time is measured continuously, and it could be a decimal, it could be an irrational number, and therefore we can say that time is any real number as long as it can be any real number as long as it's bigger than or equal to 0. And that's my domain. For my range, the output is the population, right? Population is the dependent variable, how many bacteria I have, and if you want to call it something other than population, you can do that too. And I know that the minimum amount of bacteria is 1,000. It starts with 1,000 cells. It'll never go below that because it's doubling, it's increasing. This is a growth formula. However, there is an upper limit. It will never grow past 16 billion. And so the population in terms of time is what we're measuring the range, and it has to be between 1,000 and 16 billion. And finally, population also can't be a decimal. It has to be a natural number because the number of bacteria has to be whole and it has to be positive. You can't have half a bacteria. That's 0. That's a dead bacteria because it got cut in half by something morbid. But that right there is all we have to do. We just measure the domain, or we specify any restrictions on the independent variable for the domain and any restrictions on the dependent variable for the range. In this next example, the value of one share of Lariat Studios grows according to this equation. So you're given the equation here. X is the number of years since 2010. What's the growth rate per year? So here we're looking for what is the percentage it grows by every single year. And one thing we learned is that we always express exponential functions in this form, where this number here, the growth factor, B, is 1 plus or minus R. It's plus G if we're growing, and it's minus D if it's decaying. Or instead of using G or D, I've just used R for rate because this is a simpler way of saying growth or decay rate. And of course, R is what I'm looking for. I'm looking for what is that actual rate. And here I know that, okay, the value of B is 1.10. So the value of B is 1 plus R. I know it's going to be plus, not minus, because this is a growth rate. Okay. I also know that because the growth rate, and the reason I know it's a growth rate is because it's more than 1. 1.1 is slightly higher than 1. Now, how do I find out R? Well, all I have to do, like any equation, is isolate it. So I'm going to subtract 1 from both sides, and that will cancel out the 1 on this side. And 1.1 minus 1 is 0.1. That's R. So is the growth rate 0.1%? Seems very small. And you'd be right if you're like, actually, I don't think that's true. There is one more step. We have to convert this to a percentage. And 0.1 as a percentage is 10%. You just have to multiply it by 100. So the value of one share of Lariat Studios, it looks like it grows at a rate of 10% per year. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.